Hello, everyone, and welcome back to AI Explained. I'm Clara.
And I'm Leo. Today we're diving into what many consider the heart of modern artificial intelligence, machine learning.
That's right. Last episode, we explored the foundations and history of AI, and today we're looking at the technology that's driving most of the AI advances we're seeing in 2025.
Machine learning is everywhere these days. It's recommending shows on my streaming services, helping diagnose medical conditions, and even creating that digital art I sent you last week.
Oh, that portrait where you looked like a Renaissance painter? That was definitely interesting.
Hey, I thought I looked distinguished. But seriously, machine learning seems almost magical sometimes. I'm really excited to break it down for our listeners today.
Let's start with the fundamentals. At its core, machine learning represents a fundamental shift in how we approach computing problems.
Right. Instead of explicitly programming every single rule and scenario, we're teaching computers to learn from data, correct?
Exactly. Traditional programming follows a simple formula: input plus rules equals output. But machine learning flips this around. We provide input and output examples, and the machine figures out the rules.
That's such a powerful concept. I remember trying to code a simple image recognition program back in college the old-fashioned way, and it was nearly impossible to account for all the variations.
That's the beauty of it. Machine learning excels at finding patterns in complex data that would be virtually impossible to code explicitly. And it's deeply rooted in statistics and probability.
Which explains why machine learning really took off once we had massive amounts of data and computing power, right?
Absolutely. The process is inherently iterative. Models start with random guesses and gradually improve through training. It's a bit like how we learn through practice and feedback.
So there are different types of machine learning. The first one I've heard about is supervised learning. How does that work?
Supervised learning is probably the most straightforward type to understand. You provide the algorithm with labeled examples, like images with tags saying cat or dog, and it learns to recognize patterns associated with each label.
So it's like having a teacher who shows you examples and tells you what they are, and then tests you on new examples later.
That's a perfect analogy. There are two main types of supervised learning tasks: classification, where we predict categories like spam or not spam, and regression, where we predict continuous values like house prices.
I use classification algorithms every day without realizing it, like when my email sorts spam or my phone recognizes my face, right?
Exactly. And regression is behind things like predicting stock prices or estimating how much electricity a city will need tomorrow.
I'm guessing data quality is super important here since the algorithm can only learn from the examples it's given.
Crucial point, Leo. That's why we typically split our data into training, validation, and test sets. The training data teaches the model, validation helps tune it, and test data gives us an honest assessment of how well it will perform on unseen examples.
Now, what about unsupervised learning? This one sounds a bit more mysterious to me.
Unsupervised learning is fascinating because the data comes with no labels or answers. The algorithm has to find patterns and structure on its own.
So instead of saying, this is a cat, this is a dog, you just give it a bunch of animal pictures and say, find some meaningful groupings?
That's it. The most common technique is clustering, which groups similar items together. Think about how your music app might create playlists of songs with similar vibes without being explicitly told what genres they are.
I noticed my grocery delivery app started grouping items in my suggested products list. I guess they're clustering my purchases to figure out what kind of shopper I am.
Most likely, that's called customer segmentation, and it's a classic use case. Another important technique in unsupervised learning is dimensionality reduction, which helps simplify complex data while preserving important patterns.
I'm trying to think of a real-world example for that one.
Think about recommendation systems. When Netflix suggests shows, it's not just using simple categories like comedy or drama. It's analyzing hundreds of subtle factors and patterns in viewing behavior, then reducing that complexity to make meaningful recommendations.
Let's talk about reinforcement learning. This is the one that feels most like how humans learn, through trial and error, right?
Exactly. Reinforcement learning involves an agent learning to make decisions by taking actions in an environment and receiving rewards or penalties. It's fundamentally different from the other approaches.
That reminds me of how I learned to cook. Lots of burnt meals before I got it right.
And just like you eventually learned which techniques led to delicious meals, reinforcement learning algorithms discover which actions maximize their rewards over time.
I remember when AlphaGo beat the world champion at Go in 2016. That was reinforcement learning, wasn't it?
Good memory. Yes, and since then, we've seen incredible advances. Today's reinforcement learning systems can control robotic arms with human like dexterity, optimize complex systems like data center cooling, and even generate realistic video game characters that adapt to player behavior.
Last time I tried to play against an AI in a strategy game, it absolutely demolished me. I guess I should blame reinforcement learning for that embarrassing defeat.
Probably. But remember, those systems often trained for the equivalent of thousands of years of gameplay. Give yourself a break.
You mentioned data earlier, and I've heard the phrase garbage in, garbage out. How important is data quality in machine learning?
It's absolutely critical. In fact, many AI researchers will tell you that having high quality data matters more than having the most sophisticated algorithm.
Really? That's surprising. I would have thought the algorithm was the most important part.
That's a common misconception. Think of it this way: even the best chef can't make a gourmet meal with spoiled ingredients. Similarly, even the most advanced algorithm can't produce reliable results with poor data.
What makes data poor exactly?
It can be incomplete, inaccurate, outdated, or perhaps most problematically, biased. For instance, if facial recognition systems are trained primarily on images of light skinned faces, they'll perform worse on darker skin tones.
I remember reading about a healthcare algorithm that was unintentionally discriminating against Black patients because it was trained on historical healthcare spending data, which reflected existing inequalities in access to care.
That's a perfect example, and these data issues extend beyond bias concerns. Data collection is expensive and time consuming. Proper labeling requires expertise. And with privacy regulations like GDPR, there are legal considerations around what data can be collected and how it can be used.
Once we've trained our machine learning model, how do we know if it's any good? Are there standard ways to evaluate them?
Absolutely. And evaluation is crucial. You wouldn't release a product without testing it first, right?
Not unless I wanted angry customers. So, what metrics do we use?
It depends on the task. For classification problems, we might look at accuracy, precision, recall, and F1 score. For regression, we might use
You
mean
couldn't
squared
persuade
error
me.
or
Give it
R squared values.
Hang on, precision and recall? Could you break those down a bit?
Sure. Precision measures how many of the items your model identified as positive were actually positive. Recall measures how many of the actual positive items your model correctly identified.
Oh, so there's a trade off. Like, I could build a spam filter that catches every single spam email, high recall, but might mistakenly flag some legitimate emails as spam, lower precision.
Perfect example. And the right balance depends on your application. In medical diagnostics, you might prioritize recall. Better to have some false positives that you can rule out with further testing than to miss actual diseases.
Are there any other challenges in evaluation?
Definitely. Overfitting is a major one. That's when your model performs great on training data, but poorly on new data because it's essentially memorized the examples rather than learning general patterns.
Like a student who memorizes answers to practice questions but can't solve new problems on the test?
Exactly. And on the flip side, underfitting happens when your model is too simple to capture the complexity of the data. Finding the right balance is part of the art of machine learning.
As powerful as machine learning is, there must be some limitations. What can't machine learning do well?
Great question. Despite all the hype, machine learning has significant limitations. Current systems struggle with causality. They can find correlations in data, but can't determine cause and effect relationships.
So they might notice that ice cream sales and drowning deaths both increase in summer, but wouldn't understand that they're both caused by hot weather rather than directly related to each other?
That's a classic example. They also typically require large amounts of data. They're not efficient learners like humans. A child can learn what a giraffe is from seeing just one or two examples, but a machine learning model might need thousands.
And they don't have common sense, right? I read about an image recognition system that could identify a bird perfectly in a normal photo, but got completely confused when the bird was shown upside down.
Exactly. They lack the broader understanding of the world that humans have. They're also generally narrow in their capabilities. A system trained to play chess can't suddenly decide to learn poker instead.
I've also heard concerns about interpretability, that some machine learning models are black boxes, where even their creators don't fully understand how they reach certain conclusions.
That's a major issue, especially in high stakes domains like healthcare or criminal justice. There's active research on explainable AI that aims to make models more transparent, but it often involves trade offs with performance.
Let's wrap this up with a look at where machine learning is headed. What excites you about the future of this field, Clara?
So many things. One area that's really promising is few shot and zero shot learning, developing models that can learn from very few examples or apply knowledge to completely new tasks.
That would be huge, more like how humans learn.
Absolutely. I'm also excited about multimodal learning systems that can process different types of data, text, images, audio, all together for a more holistic understanding.
I've been playing with some of those creative AI tools that generate images from text descriptions. The way they understand both language and visual concepts is pretty mind-blowing.
And they're getting better every month. Another important trend is federated learning, which allows models to train across multiple devices while keeping data private. It's a potential solution to some of the privacy concerns we discussed.
That sounds promising. Any other developments on your radar?
Energy efficiency is becoming a major focus. Current large models require enormous computing resources and energy. Researchers are working on more efficient approaches that could make advanced machine learning more accessible and sustainable.
We've covered a lot of ground today. Let's recap what we've learned about machine learning.
We started with the fundamental shift machine learning represents learning from data rather than following explicit programming. We explored the three main types: supervised learning, which learns from labeled examples; unsupervised learning, which finds patterns in unlabeled data; and reinforcement learning, which learns through trial and error with rewards and penalties.
We also discussed how crucial data quality is, maybe even more important than the algorithms themselves, and how biased or poor quality data leads to problematic results.
Right, and we talked about evaluation methods like precision and recall, challenges like overfitting and underfitting, and the current limitations of machine learning systems, particularly around causality, data efficiency, and interpretability.
Machine learning really is the engine driving modern AI forward. It's incredible to think how far we've come in just the past decade.
And we're just getting started. In our next episode, we'll be diving deeper into one particular branch of machine learning that's been responsible for many of the most dramatic breakthroughs: deep learning.
I can't wait to explore neural networks and how they're revolutionizing everything from language processing to image generation.
That's right. We'll unpack how these brain inspired systems work, why they're so powerful, and the exciting innovations they're enabling.
That's all for today's episode of AI Explained. If you enjoyed this breakdown of machine learning, please share it with friends or colleagues who might find it helpful.
And don't forget to join us next time for deep learning, neural networks, and beyond, where we'll tackle the technology behind everything from ChatGPT to those AI-generated images Leo keeps sending me.
Hey, you said you liked that one where I was reimagined as a Renaissance nobleman.
I said it was interesting, not that I liked it. Anyway, thanks for listening, everyone, and we'll see you next time.